Got my headset. Yep, welcome back. And welcome, hello everyone, good evening, good morning, wherever you are in the world again. Okay, let's redo that. So, hello everyone, and welcome again to Freaky Physics. We are live today with another lesson here today for we're gonna actually continue the lesson from last time about circular motion and rotational motion rather, and then we're gonna continue with these problems that were sent over from last time. Okay. We're gonna start in about a minute. Then okay, let me just check the actual. Okay, I'm just listening to myself. I think the sound is decent, but let's adjust the mic a bit. All right, let's try that out. All right, and now I'm gonna join the class. All right, that means okay. All right, so let's go in. There's my. Okay, I'm already in. We're still waiting for the student to join. We still have the same student from before, so we're gonna do Gita today. Today, okay, she also sent a few new problems, but I want to finish those. Hi, Gita, you're here. Good afternoon, and how's everything today?
Everything's good. How about you?
Doing well, thanks. Thanks for asking. All right, so we still have a few questions to go through from last time, and then you sent me these new problems. So I gotta ask you, would you like to go through that problem from before, or just
Yeah, I would
okay?
like to finish it.
All right then. So let me just get on to the board. Let me share that with you first.
I love the new background.
Oh, thank you. Just well, I'm a one-man team here, so I had to use AI to generate the background. It's pretty nice, I think. Yeah, thanks for the
Yeah.
feedback. All right. Also, okay. So let's start then. Let's start with that. Okay. So first of all, let's go to this. Um. So again, last time, when I pointed it out, B, we cannot actually answer B without invoking this equation for uh what's this? For wind power. Okay.
Yeah.
All right. So let's just go straight here to C. We don't actually need that the answer to B in order to get this property done. Okay. So let's take a look here. You're going to estimate the distance that the airboat travels to reach the maximum speed. So the easiest way to do this is to look at the graph and see what type of graph it is. This is a velocity time graph. So that means the area, the distance traveled, or the displacement. I'll just say distance in this case. In fact, no, I'll just go say displacement. Okay. So the displacement here is equal to the area under the graph. In other
Right.
words, it's this area here. Okay. All right. So with that in mind, we're looking to when we got to the maximum velocity. This is our maximum velocity here, right? So in other words, we're looking for this whole area here, and I'm gonna particularly do this. I'm gonna do that. Okay. Why? Because here we can see that we have this bottom area here. We'll call this A1, and this top area here A2. Okay. Okay.
How do we find the second area then?
Now, yeah, that's the next question. How do we actually find it, right? But let's take a look first at the command term. The command term here is estimate. That means you don't need an exact answer. That means in this case we can get an exact answer for A, right? But A2 can be an approximate answer. Okay. Now, so now that we know that we can approximate that, I'm going to show you another trick. Okay. So instead of doing it like A1 and A2 like that, I'm going to do it like this. Okay. Uh, I'm going to do it like this. And then I'm going to do this. That's kind of bad. This should be a bit lower, like here. Okay, like there. And then I'm gonna do another one here. And okay, there we go. We have like 4 areas, right? In this case, we have A1, A2, A3, and A4. Okay. Now, the reason we're gonna do this into 4 areas instead of those two earlier is because we can more easily estimate these shapes. A is a triangle,
Yeah.
right? A is a triangle. A2, A3, and A4, they're all um, trapezoids. So all of these are trapezoids. Okay. Now, if you don't know the formula for a trapezoid, what you can do further is you can break it down into these areas again. Right?
Yeah.
Okay. So what can we do here? We can now estimate this part to be a triangle, this part to be another triangle, and this part here to be another triangle. So we have 1, 2, 3, 4 triangles, and then 1, 2, 1, 2, 3, 4 rectangles. We can now estimate the area from there. Okay.
Yes.
All right. So uh let's just do this quickly. What's A1? This is going to be 10 times, let's say,
Hmm.
9
We
point.
don't
Go ahead.
we don't even have to do it. I just put this question because I wanted to see how accurate I have to estimate.
Oh, okay.
Like
The idea
I
here now, okay, so once we go there, so we're going to do that idea. So because it's an estimate, um, the reasonable, I'll just say here, reasonable estimates, okay, estimates are approximately 10% plus or minus 10% of the actual value. Okay. Now, what does that mean here? That means if we're able to get a really good estimate of the shapes, and here if we do this triangle, that's less than 10% out. So is this, and so is this, right?
yeah.
Okay. So keeping that in mind, because all of these, so basically, there we go. You see that this area here, this small area here, this small area here, that's less than 10% of the full area. So this is already a reasonable estimate.
Okay.
All right. So, uh, so we don't have to go through the answer anymore, I guess, as long as you know how to do it. Yeah.
Yeah.
All right. Um, let's take a look now. We're estimating the mass of the airboat here, right? Um, the easiest way to do this is wait, do we know something from A? Let's see first. I forgot if we know something from A. Yes, we do. We know, actually no, we need the answer in B to find that force. Okay?
And for the first question,
Mm-hmm.
estimating the mass is a specific number.
Yeah. This part, right?
Where we have to use, um, there was, I think it was 240. The estimate that
240.
the mass of air.
Okay, the mass of air. So let's just put that there. Okay. Uh, so let's just say that the mass of the air is how much again?
I think it was 240.
240 kilograms. Okay.
Yes.
All right. So that makes some sense in terms of the actual numbers. Uh, okay. Propel density. Where is that? Okay. So, hmm. Is this okay? The rope is anti the variation of the speed of the airboat is here. Now, uh, we're gonna do three things here from the way I can see it right now. Let me see if it's gonna work first. Okay. Um, we know here in A that there is a force acting on the air. And we know the mass of the air. Yeah. We know the mass of the air. And we know the change in the velocity of okay, I think we can do it like that. Right. So the easiest way to do this is to use Newton's third law. Okay.
Yeah.
Okay. Uh, how do we do this? We're now gonna do force on the air is equal to let's put the negative sign here to make it complete. The force on the boat. Okay. Now that we know this, let's just do ma. That's gonna be equal to ma as well, but we'll put air here and then air boat here, right? Now the mass of the air, that's gonna be 240 kilograms, right? We don't know
Yes.
the mass of the boat, so we'll call that m. And then here the acceleration will be this will be something over some time, and this will also be something over some time. We don't know that time, but we do know that this happens over the same span of time. So the times basically cancel out. Okay? So we don't need to know rather, what the actual value is. We know that it's going to cancel out. So the next part here, this would be the change in the velocity. The thing in the bracket that we didn't write yet. Okay? So because that's a change in the velocity, we're now going to look into both the graph and the given information. So going back up here, for the air, it starts from rest and then goes to 20 meters per second. So that's 20 minus 0 here. Okay, so let's write that here. 20 minus 0, right? Now for the boat, it's going to move the opposite way. So let's not forget the negative here. There's a negative here. But it's going to move in the opposite way here. So let's put another negative sign right here, right? Which way is it going to go though? So it's... Now we look in the graph for the boat. We go from 0 to 18, right? 0 to 18. Okay? Okay, so 0. So that's gonna be negative 18 minus 0. So that's gonna give us, well, that makes it easy to find because once that's done, we can now find the mass. So the mass is equal to 240 times 20 over 18.
And why isn't the velocity of air in the boat the same?
Um, well, the easiest way to explain that is because the boat is so much more massive compared to the air for some particular part. Well, at least a particular section of air, right? So what the boat is doing basically is the boat is pushing the air. So it starts off with a little bit of uh how to say that?
Also, the boat isn't moving because it's tied. No?
Okay, at the beginning it was tied, right? But here it's mentioned here that the boat actually is untied right there.
Okay.
Okay.
Right.
All right. Now, in this case, this is gonna be the long. Well, not the long. This is gonna be the incorrect way to do it though, because what we're doing here is we're doing it over 40 seconds, right? Okay.
Yeah.
Now, the better way to do this, and it's gonna be much better if we do it like this, is we still do this third law, okay, and we still do the same thing for we still do the same thing here for the air. But earlier, if you really went back into here, if you go back to the idea here, that time for the air to move from 0, okay, from 0 to 20 meters per second relative to the boat, it doesn't really say how much time this takes, right? That's our problem. It doesn't say how much time it takes. So, okay, let's go back. So we still have to do this as some time t. Okay.
Yeah.
Okay. Now here though, we can actually guess the acceleration of the boat, at least initially. We can get this acceleration from the slope, of the graph at the beginning, right about here. So right at this area, we can find the acceleration. Acceleration here is equal to, well, we can easily guess this. This is 10, something over 10 seconds. And then that's going to be around 9.8, 1, 2, 3, 4, 5, 9.6 over 10. So our acceleration here is 0.96 meters per second squared. Okay, so we're gonna put that value in here. So 0.96 meters per second squared. And again, we just, okay, uh in this case, our, okay, let's do it in the better way. So that's gonna be 9.6 minus 0 over 10 seconds. So this is going to be also over 10 seconds. So that 10 still cancels out, right?
Yeah.
Okay. So so either way, we get the same thing. So the mass will be equal to 240 times 20 over 9.6. And that's our final answer there. Okay.
Okay.
All right. So what's that going to be? Let's just put that in the calculator real quick. 240 times 20 divided by 9.6. That gives us 500 kilograms. Which is a
Okay.
reasonable estimate for the mass of a boat. Okay. All right.
Yes.
Okay.
So we,
All right. Any questions?
we just take the data from the graph and
Yeah.
estimate.
Yes, that's right.
Okay.
Okay. Now let's go to D. The fan is rotating at 120 revolutions every minute. Calculate the centripetal acceleration. Now the problem here now with centripetal acceleration is your this is your um this is your omega, right? Okay. Now the omega here is already given, but you have to express in radian per second. Okay, so that means 120 revolutions will be 120 revolutions per minute. That's gonna be 120 times 2 pi radians, right? All over
Times
60
the
seconds.
value. Right.
So that's gonna leave us with 60, 120. That becomes 2 times 2 pi. That becomes 4 pi radians per second. Okay. Now we're gonna keep this as the as the irrational number for now, and then we will do our final estimate at the end. Okay. Now that we know our omega, what's the centripetal acceleration? This is not rotational motion anymore. This is circular motion. So we're gonna do centripetal acceleration. That's going to be equal to
AR.
omega squared r. Okay.
Uh,
Okay.
how do we?
All right. I'm gonna discuss this before we continue. Okay. But anyway, what we're gonna do is we're gonna put this value in here. We know the radius of the fan. We just put the value in. So now I think I gotta answer this question. What's the difference between uh, centripetal acceleration and angular acceleration, right?
Yeah.
Okay. The easiest way to do this is with the diagram: centripetal and angular acceleration, right? Okay. The difference here is when we do this, okay, we're gonna do a very simple case of a stone on a string, and this stone is rotating that way in a circle, right? Okay. Now, centripetal acceleration, AC, is going to be directed that way. Okay. And in this case, the centripetal acceleration would have units of meters per second squared. Okay. However, the angular acceleration is going to be directed this way. So angular alpha, not AA. Yeah, so that's gonna be your alpha. Okay, it's gonna be directed this way along the circle, and the unit will be in radians per second squared. So you can see that it's a slight, it's a big difference in this case. Okay, so you have to be careful whether we're talking angular or centripetal acceleration.
But when we dealt with planets,
Uh-huh.
we acknowledged that we use centripetal like formulas,
Mm-hmm.
but we also acknowledge that the acceleration is
Yes, that's right.
real.
Okay, so
So,
the problem now between the two accelerations in this case is basically knowing which one to use, right? Now, when do you use the centripetal acceleration? You use this for centripetal forces. That's another difference. Okay. However, for this, for angular acceleration, you will use this for torque.
but how do we differentiate this?
Okay, it's okay. So that's okay. The way I can see this, and I see where this can get confusing. Uh, okay. The way I would see it is like this. Okay, when if we're talking about the forces that are causing it to turn in a circle, so yeah, let's write it here. This is where do we put that? Let's put that here. Okay. So this is about forces causing circular motion. That's the word here. Causing circular motion. Okay. Now,
Yeah.
the other one, the alpha, we're not talking about forces causing the circular motion anymore. What we're dealing with here is um, the rotational equivalent of Newton's laws. So this is still, even though this one is still talking about uh, so the first one, even if we're still talking about things going around in a circle, once we talk about forces, it's more linear and it's causing the circular motion, we use centripetal acceleration. But once we're talking about how fast it actually rotates, that's when we use the centripetal, or rather the angular acceleration. Does that kind of make sense?
Uh, I understand when we use centripetal, but the other ones, the angular motion, is
Yeah, it's still about
is there
it's go ahead, sorry, go ahead.
sorry, is there like certain questions involving like certain
Oh,
things that
okay.
we
So this I don't think you've learned it yet, but this will involve when you get angular acceleration like this, you will start calculating torque and angular momentum. What else? And moments of inertia. Whenever you see these terms, you have to use alpha. Okay.
okay.
These are the. Have you studied these yet?
We just started.
Just started. Okay. I believe you
Yeah.
may have started with torque, right?
We mentioned it, but we actually started with
Moment.
angular momentum.
Angular
And
momentum.
these.
Okay. Um. Okay. So we start with angular. So basically, I think you're gonna move this way as you do the discussion. Okay. So angular
Yeah.
momentum to torque to moment of inertia. Um. But yeah, basically, once you get to these terms, that's when you use angular acceleration. Is that clear?
Yeah.
And okay, just notice something. Somebody just spammed me on the chat
Uh,
box. Okay. Uh, all right. So I think that's done. That's the last question there. Let's go to the next, to the ones you sent over. Okay.
okay.
Uh, okay. Which one do we start with? Okay, let's start with the loudspeaker question. You know what? I think it's gonna be faster if I do this. Okay, so here's the first problem. We'll get B and C in a while. This is B. Okay, so while I'm putting B and C in here, let's read the problem real quick. So you have two loudspeakers, A and B. They're equally equidistant from the same microphone M. They're equidistant, okay, or initially equidistant. And
Mhm.
then what's gonna happen? The frequency and intensity emitted by A and B are the same. So same tone, same loudness, right? A and B emit sound in phase as in that position. A is fixed. B is moved slowly away from M along the line MP. So going towards P, right? Going towards P like that. The graph shows the variation of the distance traveled of the variation with distance traveled by B of the received intensity at M. Okay, so let's take a look at A. Explain why the received intensity between um, varies between maximum and minimum values. Okay, now
Yeah.
what's your answer here before we move on? Before I tell you what the answer is, you have anything?
And I didn't understand why it varies.
You didn't. All right, so let's just go through the idea. First of all, let's go back to interference, right? And the fact that we have destructive and constructive interference. So what I'm going to do is I'm gonna assume for now that here A and B, they are, because they have the same frequency here and they're equidistant from M, that these, I'm gonna draw one, two waves only to make it more visible like that, yeah? And I'm gonna draw one, two like that, okay? So in this case, the waves arrive in phase, right? Waves
Yeah.
arrive in phase. So what happens here? Constructive interference. So it's loud, right? So constructive
Mm.
interference, and we know what happens when we have constructive interference. The sound becomes loud, right? Okay. Now
Right.
I'm going to put B here, right? I'm going to change the color, red. I'm going to put the here so that when it emits its sound, one, two, and a half. That's two and a half waves compared to one. So when we're doing red, what do we get? They're out of phase, right?
Yeah. So
Okay.
deconstruct.
Yes. So destructive interference, right?
And why do we draw them as such instead of like the sound waves, like round?
It's actually we can draw them as sound waves, but it's a lot easier to see the wave as a transverse wave as compared to being a longitudinal wave, right? So because of that fact that it's easier to draw transverse waves, we just draw them like that to help represent our longitudinal waves. It's just a representation, but we still know that it's a longitudinal wave. Okay. All right. So
And
go ahead.
how do we know it moved? B moves exactly the distance to make it a second
Because
interference.
the idea here is it's moving constantly, so it's going to eventually hit that point where we have destructive interference. What do I mean by that? Now if we look at the third point, let's say we have our third point here, and I'm just picking these at random, but if I one, two, three, I'm drawing like that, it's back to phase, back in phase, right? So we have
Yeah.
constructive again. Now what's happening here is this is a continuous process, so it's gonna start, first of all, it's gonna start with constructive interference, then it's gonna start acting a little bit constructive, a little bit destructive, until we get to this point here where it's all destructive. Then from all destructive, as it moves back slowly and slowly into being constructive until we get to this point, constructive interference, right?
Mm.
Okay, so this only explains part of it though, because that's three marks, right? This thing we did only explains two of the marks. The third mark is explaining why we don't get to, why a graph isn't like this. You would expect something with destructive interference to look like this, right?
Yeah.
Okay, but it's not. The reason for that is because um, here, wavelengths equal, right? Sorry, not wavelength. Amplitudes are equal. So because they're
Mm-hmm.
equidistant. So actually, I'm not gonna do it here. I'm gonna do it right here. So let's go back to blue. If the amplitude here, let's use the small letter a for amplitude here, and actually no, yeah, amplitude here, and it's gonna be amplitude here, amplitude a here, and amplitude a here, right? Now let's say that
Yeah.
the amplitude here at m is b. Let's make just to keep the letters consistent. Okay, the amplitude here from this blue one here from earlier is still b, right? But when we get, but because now on the second one, on this red line, b would be somewhere here. It's going to be smaller than b here. So we can call this now c, which is less than b, right? And furthermore, if we go to here to a, because again, our loudspeaker is now farther away from the microphone, um, let's now say that in this case, the amplitude here is now d, right? And d would again be less than c. Okay, so what happens when the two microwaves, when the two speakers are in their initial positions, it's constructive interference. Then when we get to destructive interference, it doesn't totally get do destructive interference because the amplitude here is gonna be smaller than the amplitude here from A. So it's only partially destructive.
Okay.
Okay. Then also here, when we get to here, it's now constructive, but because the amplitude here is now smaller, it doesn't go as high up as before. Okay. So how would we answer this for the 3 marks? First mark is saying, I'm gonna do bullet points in this case, yeah? Okay. The first mark is for saying, the intensity, wide receive intensity varies between maximum. Okay, so the maximum values are from constructive interference. Then you can continue from there. You can add more detail, but we can just add, for now, constructive interference. Then add some more detail afterwards, right? Then the second mark
Yeah.
is for saying the minimum values are from destructive interference. Okay, and dot dot dot. Okay, and then the last one is the variations in amplitude due to distance from m. Okay, causes how to say that, causes the pattern of changing maximum and minimum values, or I can just say max values for here. Okay, all right, so those are the 3 marks, and that would be okay. And now, what would I expect you to write here in an actual paper? You can still get 2 marks, I guess, if you run out of ideas. The first two should be by default there. Okay.
Okay.
All right. Now let's go to B. State and explain the wavelength of the sound measured at M. Um, let's go back to the graph here. Okay. So basically, we have constructive interference here. The path difference here. So path difference is equal to 0. Okay. Now, and then the second part here is here. This is the next point of interest. This here is the path difference equals 1 wavelength.
Mm,
Okay. So you can already see what 1 wavelength is. That's gonna be approximately 28 centimeters or 27 centimeters. Yeah. So um so that's the explain part. So State would be lambda is approximately 27 cm, because um the first peak's path difference is 0, and second peak represents a, a lambda path difference. Okay, there. That gives you your 2 marks. All right.
Mm.
All right. Question there? Any questions there?
No, but I never thought of that to
Ah,
do that.
okay. Uh, a lot of students, in fact, when I first encountered this problem, I had to really think about this like for like 30 minutes before I could answer it. When I first encountered this, and then when I realized, oh wait, that's the idea. Okay, easy enough, right?
Yeah.
All right.
So we're just looking at the distance and then finding the.
Mm-hmm.
But if what could we use the dip for to calculate?
That's if you're gonna use the dip, you can actually do the same thing. So here, this is gonna be the path difference is half a wavelength. Okay, and here would be 3/2 of a wavelength. So this would be
Right.
2 wavelengths. This is gonna be 5/2 of a wavelength. Okay. Now, what can you do? You can always use any 2 points. You can use this point and this point. We can use the points that we've used earlier. You can use these 2 points. You can use these 2 points as long as you know what the path difference is. Okay. So
Okay.
if we use these 2 points, what's our path difference? It's still gonna be lambda.
Right.
Okay. All right. Anything else you'd like to ask?
No, I understood it.
Okay.
Thank you.
All right. Great. So let's move on to the next question. C. B is placed at the first minimum. The frequency is then changed. Okay. Hold on. The frequency is then changed until the receiving intensity is again at the maximum. So this is a little bit different now. Okay. So basically, let's draw this on the side first before we answer. So this is A, this is A, this is M, and this time B is no longer here. B is gonna be somewhere here. Okay.
But what
So
does it mean? Placed at the first minimum.
okay. So basically B is placed here so that this is on the 1/2 lambda path difference. In other words,
Okay.
if we look at the graph, here, we B is positioned here. Okay. All right. So let's just continue. So we know a couple of things here. Now, what's happening here is currently we now have a frequency 1 wherein this leads to a minimum, right? And then you change from frequency 1 to frequency 2, which leads to a maximum. Okay, I better move that a bit. Okay. So again, so here at B, it starts off with the frequency 1, and then you change it to frequency 2. At frequency 1, you have a minimum. Frequency 2, you have a maximum. So what are you going to do here? Show that the lowest frequency at which the minimum, the intensity maximum can occur is about 3 kilohertz. So basically, what this is saying is now, hold on, let me think about that. Okay, that you have to think of this as the path difference, right? Okay, this is the path difference x, and now when you change it to f2, so when f1, x was equal to 1/2 of a wavelength, right? But now that you have f2, so when you change it to f2, x is now 1 full wavelength because you now have a maximum, right? Lambda. Okay.
That's so. F1 is the first minimum. F2 is the first maximum.
Um, not exactly, but that's one way to say it. But it's not so much as you're comparing the two frequencies together. You're actually getting two different answers if you use f1 and f2. Okay, so
Yeah.
here's the thing though. Either way, we can find x here. Our x is here on the graph, right? X looks
Yeah.
like it's around 14, right? So we're gonna do that here. So that means, okay, we have just figured out that lambda 2 here, this is gonna be lambda 1 there, right? So we just figured out that lambda 2 equals 14 centimeters. Okay, now what do we do now? We do the wave equation. 300 f let's just do this here. V equals frequency times wavelength, right? So this is gonna be 340 equals the frequency 2, times the wavelength is 14 centimeters. That's gonna be 0.14 meters. This is gonna be meters as well, so that cancels out. So our frequency here, f2, will be 340 divided by 0.14. So let's put that in. 340 by 0.14, 2400 hertz. Uh, which is close enough to 3000 hertz, right? Now, if you want to get a better answer, then you can use a different value for our value here. We can use 15 or maybe 13. Okay. All right. But
Yeah.
again, because we're just estimating this from the graph, um, 2400 hertz is close enough for 3000 to count. Okay.
Okay.
All right. Loudspeaker. Let's go to D. Loudspeaker A is switched off, and then it's moved here. Oh, okay. This is now because A is turned off and then B is moving. This now turns into the Doppler effect question. Okay. Now, you still have to say one more thing. Which one is moving? Is it the observer or is it the sound source? In this case, we
The
identified that
source.
source moving, right? Source moving. Now, we have to do this because remember, for the data booklet, there is a difference between the two formulas for whichever one is moving. If the source is moving, the formula is different compared to when the observer is moving. Okay. Uh, Data booklet. Hold on, let me just open the data booklet again. This is one of those formulas I don't memorize. Just look at the booklet and reason out with it.
Yeah.
Okay. Let's see. The Doppler effect. Doppler effect should be in C. That's okay. Here we go. C, Doppler effect. There we go. Uh, since in the Doppler effect you do have the two formulas already given to you, you just use the relevant formula. In this case, the source is moving. F prime is equal to F V over V plus or minus US, right? Again, V here, let's just make sure that we're sure here V is the speed of sound, speed of wave, okay? All right, and then the US, the S here indicates source, okay? Now, the last thing you want to do here is, before you do the calculation, is just remember again what happens. What is the higher pitched sound when the object is coming to you or going away from you? The easiest way to remember that is an ambulance. Right? How does the ambulance, where do you have the
Coming
higher
to.
pitch? Coming to you is higher, right?
Yeah.
Okay, but in this case, the object is moving away. So we are going to use the version that's going to give us the lower frequency. So moving away means F prime is less than F. Okay, now we're gonna use the values. That's gonna be F prime is equal to, what was the frequency we got? Let's use 3000 because that's the thing we're used to estimate, right? Our V, what's what's the V here? 1.5, right?
Yep.
Okay. Sorry, that's gonna be plus or minus 1.5. This is gonna be 340. 340. Okay. Now again, you want the lower frequency, so you're gonna give a smaller answer. So you're gonna use the plus version. Okay. So that's gonna be 3,000 times 340 divided by 355. Okay. So finally, calculate. Sorry, I'm missing a zero here. So 3,000 times 340 divided by 355. That's gonna give us 2,900 hertz. So f prime is equal to 2,900
Mm,
hertz.
okay.
Okay.
Okay. Okay.
All right. So that's the Doppler effect question. All right. Any questions here? Any other questions before we move on?
I understood everything.
All right. Great. Let's do this last one. Oh, it's the magnet. Which one do we do first? Let's do the magnet problem. Copy this.
Okay.
You are you okay? We go like a little bit over time, like maybe 5 minutes over time. Are you fine with it?
Uh, that's okay with me if it's okay with you.
All right, I'm fine with it as well. So let's just do it so we can finish everything. All right, so let's go here to 8, this question, and let's get the questions in as well. That, and next one. Okay. Okay, so let's take a look at the situation now. Um, okay, so let's read it first. So you have a magnet falling into this coil of wire, and the coil of wire is attached to a voltmeter, right? Is there
Yeah.
anything else given? Not really, just that, right? So the variation of time with time t of the EMF induced is shown here. Okay. All right. A. Write down the maximum magnitude of the rate of change of flux linked with the coil. Okay, the maximum magnitude. Okay. Um
This I didn't know if we do the negative or the positive or do we
okay,
add them
it
up.
doesn't matter at this point because it's just the magnitude. So we don't really care about the signs. Okay.
But it's larger when it's negative.
Not necessarily. The idea yeah, so we have to look here. This is because this is the larger magnitude, right?
Yeah.
So that's what we do here. The magnet. Okay. I'll remove that. But in this case, remember that's the induced EMF. Okay. So in this case, remember that for this to happen, the induced EMF must be equal to negative um phi delta phi over delta t, right? Change in flux, largest change in flux. So where do you have um okay, is there anything else I need to know here? I think okay. Is there anything missing? Hold on, let me double check with the formula sheet. Booklet, and here we go. Flux linkage. Okay, that's it. That basically we're looking for this. Okay. There's actually supposed to be an n here, negative n here, but this part here, the rate of change in flux linked, this in symbol form is the n phi, delta phi over delta t. Okay.
Yeah.
So in other words, this question is basically asking for maximum EMF. So all you have to do is read. So the
And we don't have to
magnitude,
convert.
we don't have to convert. And let's just do, what's the question? What's the unit in the graph? Millivolts. Millivolts. And remember, because just magnitude, that's it. You don't have to put the sign. Okay.
Okay, and just to clarify,
Go ahead.
it's bigger. It's bigger when it's negative because the velocities because it's going
It's
faster.
moving
So it's,
faster, something like that. Yeah. The correct term here would be the magnetic flux linkage is changing at a higher rate. And one way you can do that is to have the magnet move faster.
okay.
Okay. Another way you can do that is for one reason or another, you're just actually increasing the magnetic field. Okay. All right. Let's
Okay.
go to 2, fundamental SI unit. Okay. For your answer in what's the fundamental SI unit? This should be you cannot say volts. Volts would be wrong because that's not the fundamental. Remember though that for volts that's basically energy per charge, right? Now the reason why I want to do it like this is because energy can be expressed in force times distance because that's work done, and then charge is current times time. Okay, but here's the thing: the force can be expressed in kilogram, in mass. Let's just do it in mass first. Mass times acceleration times distance over current times time. This is already fundamental. All of these are already fundamental because acceleration, even though it's not fundamental, the units are fundamental. So this is going to be kilogram meter per second squared, meter per I is in ampere seconds. So what can we combine? It's going to be kilogram. The meters can be combined, so meter squared. This second and this second can be combined. This becomes per second cubed. And this ampere here is by itself, so per ampere. This is the fundamental SI unit.
Okay.
Okay. However, given that it's only one mark, there is a chance that volts will be correct. Small chance. But just to be safe, we do it like this. Okay. This is the safe
Yeah.
answer. All right. Explain why the graph becomes negative.
Oh, I understood that though.
Oh, you understood this part. All right, so let's skip that. What else do we need to go through? Part 2. Part of the graph is above the T and part is below, outlined by the areas between are likely to be the same. Okay. You have an answer for this? For part 2?
Um, but they aren't the same.
Well, they're definitely not gonna be the same, but they are gonna be at least approximately the same. Okay. Okay, the reason is this because think about it, because as the magnet falls, uh it basically provides energy for the coin, right?
Yeah.
Now as the magnet goes through here, so once it starts going through here, first of all, let's go back here. um at this point, that's the north pole on the coil and this is the south pole of the coil, right? As
Yeah.
that falls. Now, however, once the magnet goes here, so that's gone here, it's now here, the south pole is here. This has to turn north and this has to turn south again, right?
Yeah.
So in other words, it flips over. But as this falls, the rate of change, actually no, it still falls faster here though. But the thing is, basically, volts in essence is just a unit of energy, right? That's where we actually kind of think about what the answer is. Volts is basically a unit of energy. So what does this mean? This basically means the energy as it falls down from above the coil is a certain value. And then because of conservation of energy, it has to be somehow balanced somewhere else. And that's where the balance here is. So this is basically the conservation of energy. Right? So,
Yeah.
all right, so let's do here. due to conservation of energy, I'll write it here. Energy. The coil, the magnet, sorry, the coil magnet system energy must not change, right? Energy must
Yeah.
stay constant. So that means the upper part, that's positive energy, the lower part, that's negative energy. So the two areas being equal means the energy gained is offset by the energy lost. Okay? And therefore it stays constant. Energy gained, top of graph, is offset by energy loss. Bottom of graph. Okay. So let's just write that
Okay.
there. All right, there we go. Okay. So is that clear?
Yes.
All right. Is there any other question that I need to do? Oh, we have one more. The the last question, the resistor. You know
Yeah.
what? When I see this problem, I always think I never teach this particular problem to my students, just so you know.
Why?
Because I want to make it challenging for them because it's all about a way of it's just basically the way you look at it. This is actually a rather simple circuit, right?
Yeah, I thought we just split it up and then we add it, but I
Uh-huh.
wasn't sure.
Right. Okay, so the EMF here is 3 volts. So what do? The EMF here should be the same, right? And then the EMF here on these two should be the same. So you have to find the overall resistance first. Um, Actually, okay, let's do it like this. What is this and this? This should be easy. This should be 1 volt here. This should be 2 volts here. Okay? Now, this means this is 2 volts across that, and this is 1 volt across that. Right? Now, that means, remember though, that this voltage here is a potential difference. So basically what you think of here is this is the difference. So what I'm gonna say here is the voltage here is actually 3 volts. Okay? Alright, so why
Yeah.
is that 3 volts? Because it's connected to the positive end of the battery. Okay? Now, because of the fact that the potential difference across R1 is 1 volt, then this will be 2 volt reading on this point. And therefore, from 2 to 1, that's going to be a 0 volt reading here. Because the difference is 2. Difference is 1,
Hmm.
difference is 2. Okay? Similarly, the difference here is 2. So what's the voltmeter reading here? Sorry, not the voltmeter reading. What's the actual voltage here? If the difference is 2, this must be 1 volt.
After it's one.
Okay? Then
Yeah.
similarly, the voltage here across is 1. So from 1 to 0. So everything makes sense, right? So what is the
Yeah.
voltage reading across this 2? 2 minus 1 gives you
One.
1 volt. So the answer here is B.
So we don't add them.
No, we don't have to. You could if you really wanted to, but the one thing that that makes this easy for me is this overall resistance is 3 on this part of the circuit. Because these two are in series, right? So that
Yeah.
means for every ohm, there's a 1 volt drop. Similarly here, this is also 3 volts, 3 ohms in total, right? So the same thing. For each ohm, there's a 1 volt drop. Okay?
Okay.
All right. So I'll just write that last bit. So the difference, difference in V equals 2 volts here. So here the difference should be equal to 1. The difference here should be equal to 1. And the difference here should be equal to 2. So that's what you write there first. Differences, and then you find the actual values. Okay?
Okay.
All right. I think that's pretty clear. Anything else you'd like to ask then?
Everything's clear.
Great, and we're
Thank you.
able to finish everything today. Great. All right. All right. So, all right. In that case, I'll just see you again on our next meeting. I think that's on Thursday, right?
Yes, I hope the time is okay with you.
Yeah,
I said it.
yeah, it's fine with me. Okay.
Okay,
So,
perfect.
all right. So I'll see you on Thursday, and you have a good day ahead. Okay.
Have a good day.
All right. Bye
Bye
bye now.
bye.
All right. So that's the end of this lesson here. We went a little bit over time, but that's totally fine as usual with me. Uh, let me just finish this. All right. So for those who are listening in, hopefully you learned something, and excuse me. Right. Whoa. Okay, so there we go. So, okay, so let's just end the lesson here. I hope you all learned something. So before we go, don't forget to like, share, and subscribe to the channel. Of course, we are on Facebook, YouTube, TikTok, Instagram, and on Twitch when we go live. Currently, just so we have an update, I'm currently trying to uh, upgrade my workflow so that I do everything by myself, basically. So once every time there's an update or there's something new, it will be posted. Hey, okay. Eh, who's this? Magenta Lion. Okay, welcome. But unfortunately, we're done with the stream. So okay. Either way, thank you for just joining in. Now, if you wanna just watch the rest of the video later on, go ahead and do so. But for now, since this is the end of the stream, I'm just gonna wish you all a good morning, good day, good afternoon, good evening, good night, wherever you are in the world. And you all stay freaky, everyone. Bye bye now.